Hmm. All right, here we are again. All right, so we have we're still in chapter 11, and so we'll pick that up. But first, we actually have a few videos today to look at, which is always fun. So the first one is something that I found for the other class that I want you to see as well. You might remember when we were talking about combinations last week. Combinations are selections of objects where the order of choice does not matter. All right, in fact, while we're reviewing, let's go back to where we were and just remind ourselves that so far what we've covered in this chapter are arrangements, where we simply take a collection of objects and change the sequence of them. And we found out that, like, for example, here with the parking garage case, we had 3 cars, 3 garages, and we discovered that there were 6 ways of parking the cars, and that each of these choices is referred to as an arrangement. And we also found out that the number of ways or the number of arrangements that we can create is very easy to calculate because it's simply equal to n factorial. Right, n factorial, there it is. And we do have this on our calculators on our phones. You recall that if you look at your phone calculator in the bottom left-hand corner, towards the very bottom left, you find it's labeled here x factorial, and that will enable us to do all these calculations ourselves without too much difficulty. We also introduced the concept of permutations. And with permutations, we're actually selecting objects from a larger group, but we're doing it in such a way that the order of choice matters. There's some reason why the order of the selections makes a difference. So, for example, when we're looking at the case of the math club, we needed to pick 3 members out of 10 to fill the presidency, the vice presidency, and the treasurer position. And we noted that each choice does matter because, for example, if I pick students number 3, 1, and 7 in that order, it means that student number 3 becomes the president, student number 1 becomes the vice president, and student number 7 is now the treasurer. And that selection, as you can see, is very different from this one. Even though it's the same 3 numbers, they're chosen in a different order. And that makes a bit difference because now suddenly it's the 7th student who's the president, the 3rd student who is the vice president, and the 1st student is the treasurer. So each of these selections, 317 and 731, are considered to be different permutations. We also saw the formula that's used to calculate permutations, and of course you can see that we can do all these calculations from our factorial operator very quickly and easily. And then we jumped, and after this, we found that when we choose objects from a larger collection in such a way that the order does not matter, we end up with what are called combinations. And the formula for combinations is a little bit more involved. For example, we did this, where are we? We did one with toppings at Haagen-Dazs. Where is it? Huh. Okay, I must have slipped it in on the other one. Hold on one second. Yes, the Haagen-Dazs example. Hold on one second. I just want to go get it. There it is. Okay, so here's the Haagen-Dazs example. So we go to Haagen-Dazs and they're having a special promotion. You can pick any 2 of the 5 toppings for free. So therefore, when you have 5 toppings like this and you pick 2, we're assuming that the order of selection does not matter because, and I mean, really what's going to happen with these choices, they're going to put them on top and you'll have your ice cream. And theoretically, at least, it shouldn't matter if the gummy bears are picked first and then the Oreos, or the Oreos and then the gummy bears, for example. So we think of these as all combinations. And I've listed out all the possibilities. And there's 10 of them, as you can see. Now, if you notice, I have G and O, gummy bears and Oreos listed. I do not separately have O and G, which is Oreos and gummy bears, because this time the order doesn't matter. So now this is where it got interesting. And I don't think we covered this in your class. I think I only did this in the 1030 section. Just as a side note here, there's an interesting historical event that took place, not that important, but when the history of statistics, this was kind of an important anecdote, because what happens here is that in this real world event, the statistician Ronald Fisher encountered a case where he was at a party, an event of some kind, and they were serving tea. And, in England at least, it's not that uncommon for people to have milk with their tea. Okay, it's a common thing in England. I don't think you see much of that here. Usually people have either lemon or sugar, or certainly tea is not that common here. But in Britain, it's fairly common to have milk in your tea. So what happened was, apparently when they brought the teas around, one lady in the party complained that the waiter put the tea and the milk in the wrong order. I think the problem was that she said he poured the tea into the milk or something. Anyway, there's something about it she didn't like. But the bottom line is that she claimed that she could tell the difference between whether the tea was poured first and the milk second, or the other way around. So if that was really the case, each possible selection of teas would then count as a permutation. But if the order doesn't matter, and if you can't tell the difference, then each choice is a combination. So the statistician Ronald Fisher was at this party. He's a very famous figure in the history of statistics. And so, being Ronald Fisher, he decided it might be fun to conduct an experiment to see if this lady really knew what she was talking about. So, this is the experiment that he devised. He went to the back in the kitchen and he had them prepare 8 cups of tea. In half of the cases, the tea was poured first, followed by the milk, and in the other half, it was the other way around. And so the experiment consisted of bringing out the cups and asking her to taste each one and identify whether the milk was poured first or the tea. So he figured if she knows what she's saying, if this is for real, then she should get most of them right. So it turns out, and I guess there's no reason not to spoil the surprise, but it turns out that she actually got all 8 of them right. So he concluded that even though there's still a remote chance she could have gotten lucky, that she obviously knows what she's talking about, and she could really and truly tell the difference between whether the tea was poured first and the milk was poured first. So this proved to be a very important result, because he went on and he wrote or developed a lot of other results from this experiment. So anyway, I did manage to find a video which talks about this in great detail. So I did show it to my other class. I want you guys to see it today because it's a lot of fun. And let me just go get it right now. Here we go, the lady in the teacups. And let's check this out. All right, I'll stop the screen sharing and then let's watch. We have cables. All right, so are we done? Good. Excellent. So good for her. She did know what she was talking about. Yes, it was. But that's a very famous story in statistical history, because Ronald Fisher was one of the really big heavyweights in statistical history. A lot of the results that we use today were developed by him. So he's very, very well known. So it figures that somebody like that, when he ran into the situation at a party, instead of just laughing it off, he would, of course, be the one who would come up with an experiment to see if this could possibly be true or not. Now, I don't know if I could tell the difference, and I think most people probably couldn't. But for whatever reason, this lady could tell the difference. And so it mattered to her a great deal which one was poured first. So that means from now on, maybe the waiter should be more careful when they pour her tea. But yes, it did lead him to do a lot of thinking about how could you actually prove at some point that she does clearly know what she's saying when it is 8 out of 8 enough, in other words, to prove. Now it turns out I did the calculations myself. In order for her to have gotten all 8 of them correct by pure dumb luck. In fact, let me just throw this into my calculator for a second. Um, the probability of getting this by pure dumb luck would have been 0.003, in other words, 0.4%. Okay, how likely does that sound? 0.4% chance that she got it by pure luck. I would say that means she knew what she was doing. Okay, yeah, the chances of that being done by, it would be like getting onto a multiple choice test and getting all it right when you didn't know what you were doing. It's not likely. All right. Well, anyway, I thought that was our fun for the day. Now, we also have this other video. Now, the reason why we're going to show this next video and also the lady with the tea is because we're now done with our discussion about combinatorics, meaning arrangements, uh, permutations, combinations, and we're ready to start looking at actual probability theory itself. And so we've got this video that I'd like you to see, which actually discusses or introduces the field. All right. And then when that's done, I've got another amusing video, which is all about, again, probability theory, but in a very fun and clever way. So first, let's check this one out. All right, here we go. I'd like to find the best model of math and science. Yes, we will. But I'm sick today.
Professor, we didn't get the link.
Oh, yeah. You know what? I just realized I sent it to the wrong spot. Hold on. I'm glad you, well, okay, thanks. You know why it's this chat box thing? It's really annoying because it just, yeah, it goes to the wrong place sometimes. So, all right, hold on 1 second. Let me just send it back. One more time. It's easy. Yeah, here we go. All right. So is it there now?
Yeah.
Okay, good. All right, let's check it out. All right, are we done? Well, okay. Oh, yes. Okay, good. So that was kind of a lot of information and taken all at once. That's okay. It doesn't really matter because we're going to cover all those topics very slowly and very carefully. So by the time we're done, um, you'll really understand what they were going through. Now, of course, there's a lot of stuff there and it was a lot to absorb, but in small stages, we'll get through all that material. And when we're done, I think you'll agree that this is a very interesting area of math. But I have one more fun video here before we dive back into the new material. This one involves birthdays. So it turns out that you might be surprised to discover how likely it is that two people in a group have the same birthday. It might seem not likely given that there are 365 days in the year, and of course 366 during leap year. So what I usually do when we're meeting in person is I have everybody in the room tell me their birthday, just the day and the month, not the year. And I write it down on the board, and almost without fail, before we get very far, there's two people in the class who have the same birthday. Now, I don't think it's possible to do that here, but you start writing them down, you figure, well, it'll take forever. There's no way two people, because we only have 30 people in the room or whatever. It turns out that if we have 23 people in the room, the chances of two people having the same birthday is 50%. It's very difficult to imagine how this is possible given how many days there are in the year. This is one of those paradoxes that you might run into that we can explain with probability theory. So why don't we watch this, and you'll want to be prepared to be amazed because it's absolutely true. So let me grab this one and send it to you. And then we can get back to our notes. All right, here we go. Check this out. Oh, you do. Absolutely. It's very common. Very interesting. In fact, I'm quite confident that sooner or later you will find an excuse to mention this to somebody that you know and say, by the way, did you know that if there's 23 people in the room, there's a 50-50 chance that 2 of them have the same birthday. So, and you can see they did go through it. Now, if you notice when they were talking about how to figure it out, it reminds us a little bit of the way we were explaining how to park the cars in the garage. Remember, you had 4 in the first garage, 3 in the second, 2 in the third, etc. So combinatorics is a very interesting way of going about solving these types of problems. And if you notice, they had to kind of dance around it a little bit. Instead of figuring out the probability that 2 people have the same birthday, instead they made it easier by figuring out the probability that 2 people do not have the same birthday and subtracting that from 100%, because of course, those are the only 2 possibilities. Either 2 people do or they do not have the same birthday. And so sometimes we can simplify problems by approaching them from a different direction. In fact, one year when I was doing this in my class, when I asked people to write down or tell me their birthdays and I wrote them on the board, I think only one time nobody had the same birthday. And another time, just by a ridiculous coincidence, the first 2 people had the same birthday. So we were done after 2 people. And so one day maybe I should sit down and figure out the odds of that one happening. But it would definitely, almost without fail, anytime we have a group of a reasonable size like that, 23 or above, you're going to get most likely a couple of birthdays that are the same. In fact, you may get more than that. But anyway, so I thought you'd find that it was kind of fun too. It was just obviously very cute, very amusing. It was fun, which is nice. I wish all videos were fun. Some of them are. We've had some nice ones so far, but I thought that one was especially fun. And not intuitive either. That's when math is fun, when you get results that don't seem to make sense based on your intuition. And so he did make an important point here. We're very good at doing certain things, but other areas, it's very easy to get confused, especially in the area of large numbers. This is where the human mind starts to fall apart a little bit. It's very difficult for people to deal with large numbers, at least in their own heads, without using calculators. And so you can run into these so-called paradoxes where the results don't seem to make sense. But anyway, so that's enough of that. Now we can get back to actual probability theory. And so before we do any actual calculations, we're going to start out by looking at or providing some background for what we're about to do. So probability theory itself is simply a mathematical framework for measuring uncertainty. That's really what we're trying to do. We're trying to take real world events and associate them with probabilities. For example, what if I wanted to know the probability that the Dow Jones Industrial Average will go up today? That might be good to know. What if I want to know the probability that it rains every day next week? What if I want to know the probability that a meteor hits the Earth? Who knows? There's any number of things that could happen at random that we would like to know the probability of. So we're going to start out by introducing what's called a random experiment. This is what gives structure to our calculations. In other words, we're assuming that there's some process taking place which is actually generating these random outcomes. And this could be a very simple situation. For example, something as simple as flipping a coin. When you flip a coin, of course, you know, when you flip the coin, that it could either come up heads or tails, and either of them is equally likely. But what you don't know is which one will actually turn up. And so with that information in hand, you could ask a question like this. Let's say I flip the coin 10 times and I want to know the probability that all 10 of them are heads. Well, that's the kind of thing that probability theory can help us understand how to calculate the probability of. So it's going to provide a structure to our calculations so that we can determine the probabilities of different events taking place. Now in the second video, they mentioned that there's really 2 basic types of probability that we could run into in practice. The theoretical probabilities are really being taken from our understanding of the random experiment. Like with the coin flipping, we know from experience or from the way the coin is constructed that there's a 50% chance of getting a head and there's a 50% chance of getting a tail. In practice though, when you flip the coin, suppose that, let's say you flipped a coin without knowing how it works. you'll come up with what's called an empirical probability, which means based on experience. All right, so they mentioned that word a couple of times. I just want to mention that the word empirical simply means based on experience. And in some cases, that's all that we have to go by. Sometimes we cannot create a theoretical framework for our calculations. And in those cases, we have to rely on experience. And so for certain areas, this is all the information that we have. In other areas, we do have theoretical results that we can lean on. So the random experiment is conducted in such a way that the outcomes, all the outcomes are known in advance. What, or at least I should say, all the possible outcomes are known in advance, but the actual outcome is not known in advance. So in other words, we know what could happen, but we don't know what actually will happen. Now, it turns out that games of chance are excellent ways of illustrating probability theory. So we're going to look at a few of those right now. Let's say, for example, we're spinning a roulette wheel. Now, if you've never seen a roulette wheel, it's a big wheel, of course, and it has numbers on it. There's actually altogether, the way it's constructed is that there are 36, numbers 1 through 36, half of which are red, and half are black. And in addition, we have these two extra numbers, 0 and 00, which are green. And the reason why those are there is to guarantee that the odds of your winning are in favor of the casino. So in other words, you have to imagine that this is cut up into 38 equal slices, I guess you could call them. And then the little ball is spun, or they spin the wheel with a little ball, and it lands on one of the slots. And let's say that's the number 3, and that's how they determine who wins. So the thing that uniquely identifies who wins is the number as well as the color, because the players can bet on the numbers or the colors. So each outcome or each number is set up to be equally likely to turn up. So therefore, each number has a probability of 1 out of 38, because there are 38 numbers altogether. So you bet your money on one outcome. You can bet on each number, you can bet on ranges of numbers, you can bet on odd or even, you can bet on black or red. There's all kinds of possibilities. But the bottom line is that each number is equally likely to turn up. And so this would be considered an experiment, a random experiment, because we know in advance there are 38 equally likely outcomes that could occur. All right, now choosing a card from a deck. Well, you've got 52 cards. Each is equally likely to be chosen. So therefore, each has a 1 out of 52 chance or probability of being chosen. And so you could, for example, ask yourself, what's the probability of getting an ace or a red card or a diamond or that kind of thing? Because you know that each card is equally likely to occur. You also know how the deck is constructed. There's 4 suits: spades, hearts, diamonds, and clubs. Might as well mention it over here. Spades, clubs, hearts, and diamonds. And of course, these are red and these are black. And then, of course, finally, we have the dice. Everybody's played with dice. Every game under the sun, or many games, require us to roll dice. And so each one, oh, by the way, I just want to mention here, as a point, interesting note here, point of English, just in case you were wondering, dice is plural, die is singular. So when you roll a single die, it's called a die. When you roll a pair of die, I mean, they're called dice. Two die, each die is individually a die, but when you have two or more, it becomes dice. So everybody knows how dice work. A single die has 6 numbers, 1 through 6, and of course, each of which is equally likely to occur. When we roll a pair of dice, and we don't necessarily want to go through all of this right now, but when we roll a pair of dice, there are 36 possible outcomes. And that's because there are 6 outcomes from each individual die. So when we roll the die twice, or roll the dice, 2 dice, the number of possibilities increases to 6 squared. Let's see. To turn that into a superscript, 6 squared, which is equal to 36. Okay, so in other words, every time you roll the die, again, the number of possibilities is multiplied by 6. Okay, so now we're going to look at an experiment here, a very simple case. Now, because there's so many outcomes here, we're going to focus on our attention on a case where we are rolling the die twice, but we're only focused on whether the number that turns up is odd or even. Okay, that reduces the number of possibilities so that our calculations become manageable. So suppose you're playing some kind of a game where every time you roll the die, all that matters is whether you got an even or an odd number. And so, of course, if you get 1, 3, or 5, that's an odd. If you get a 2, 4, or 6, you get an even. So what can happen in this experiment? So instead of 36 possible outcomes, now we only have 4. Okay, and what are they? Well, you might get 2 consecutive evens. You might get an even followed by an odd. You might get an odd followed by an even, and you might get 2 consecutive odd numbers. And because each die has 3 even and 3 odd numbers, each of these is equally likely to occur. That's a key detail. So we've got 4 equally likely outcomes. By the way, I do want to mention here that when you're rolling the dice and you're really looking at the individual numbers, each outcome is not equally likely in that case. In fact, let me just show you a little chart here. Let's see. Oh, this shouldn't take too long. The possible outcomes are when you roll both dice. Ooh, I don't know if I can fit all this. Well, you get the idea. You're going to have, let's see. Well, as long as I've come this far, I might as well fill them all in. Okay, 4, 1. Okay, well, I think you see where this is going. You can see there are indeed 36 of them. But what we normally pay attention to when we roll the dice is the sum. I mean, if you've ever played a game with dice, you know that the number that really is relevant to the game is the sum. So let's say, for example, you're playing Monopoly. The numbers themselves are irrelevant. What matters is the sum. So if we made up a chart of the sums that could be created here, you would see now, for example, what if I wanted to create a chart about, and that covers the number of possible outcomes of each of these sums. So let's try that real fast. And let's get rid of this ghastly green. This is what Microsoft thinks is the proper color for a table, if you can believe it. Okay, so what would we do here to come up with the probabilities of these different sums? Yeah, I know, but it's kind of hard to read it, and I don't know if it's really appropriate. I mean, imagine you're trying to create a serious table for a presentation where you work, and you come in there with green. I don't know. It just, see, the thing is, it's not that green isn't like nice, but the way they've set it up, it's going to assume that that's what you want. Now, that's the part that I find very bizarre. Like in others, I would think that 99% of the time, when you create a chart in PowerPoint, you're going to want just plain black and white. And if you want the other colors, they're up there. But to say, no, we'll start out by assuming you want green, and then you fix it if you don't like that. Well, I think that's kind of ridiculous. But that's my opinion. All right, I just realized I'm going to need more space here. Hold on one second. That's the other thing too. If I need a solid fill, it assumes I mean green. No, I want white. The purpose of the white is to block off anything that's in the background. All right, so what am I after here? You can see I'm giving you a free PowerPoint lesson. How to create a table in PowerPoint that looks right. Okay. Okay, one day you're going to need to know how to do this, most likely. All right, so in other words, the sums that you can create with these two dice would be 2 through 12. Oh, okay, well, we don't need every one of these. Now, how do you know what the probabilities are? Well, here's what happens. Each of these outcomes is equally likely. So if I want to know the probability of getting a 2, what I'm going to do is come in here and say, well, in how many of these cases do they add up to 2? Oh, just once. That's it. So that means the probability must be 1 out of 36. What about 3? How many different ways can I get a 3? Oh, look, there's these two and this one as well. Oh, sorry, what did I do? No, not this one. Sorry about that. There's 2 ways this can happen. I can get a 1 followed by a 2 or a 2 followed by 1. If I'm playing Monopoly and I need a 3 to land on Park Place, there's 2 ways this can happen out of 36. So it's not likely, but it's possible. So if I want Park Place, let's say whoever gets there next gets to buy it. I want Park Place. It's the most expensive property on the board, as you know. And so I would be very unhappy to see that it's going to be that hard to land on it. All right, now we can go through all of them in the same way and come up with all of the other probabilities. For example, 4, how do I get a 4? Well, I can get a 1 and a 3. I can get a 3 and a 1. And I can get a 2 and a 2. Those all add up to 4. So the chances of getting a 4 are 4 out of 36. And so it goes on, and I don't want to spend all day with this, but if I keep going, you'll see that it goes up to 5/36, 6 out of 36, and 7 out of 36. Then it starts getting smaller again. Oh, wait a minute, something's not right. Yeah, what happened here? Let's see, the number of ways of getting a 7. Oh, I know, I screwed it up right here. I jumped from 2 to 4. Okay. I was going to say that doesn't look right because they have to go back to the original numbers. Okay, there we go. They have to add up to 36 out of 36. That's not going to happen. Okay, so that fills in all the possible problems. And if you notice that they do have to add up to 36 out of 36, which is the same thing as 1. And so these are the odds of getting different combinations. So that shows you that unlike the case where I drew cards from a deck, where each possibility was equally likely, when I'm rolling the dice and I'm looking at the numbers rather than odds or evens, then that changes everything. So if you were to take this and break it up into evens and odds, you would see, though, that there's only 4 possibilities, of which each is equally likely to occur. Okay, so for example, if I were to highlight even, let me get these out of the way here. Let's say I wanted to really know, what does it mean to get even followed by even? That would be all of these. Sorry, no, this one. This one. This one. And then down here, I have this one, and this one. And then I've got these last 3. And how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 36. Let me just throw this in here. As an example, even results from rolling. And then we could just list them all. 2, 2, 2, 4, 2, 6, 4, 2, 4, 4, 4, 6, and then finally 6, 2, 6, 4, or 6, 6. There are 9 ways of getting even out of 36 equally likely rolls. And which, by the way, we're assuming that when in this chart, all of these outcomes are equally likely. Okay, so in other words, each individual outcome is equally likely. What's not equally likely is the different sums. Okay, so I'll just add that as an explanatory note here. Note that since the die are assumed to be weighted properly, each of these 36 possible outcomes is equally likely to occur, and therefore has a probability of 1 out of 36. Okay, that's an important detail. Each one is just like it would be no different than picking cards from a deck, except let's say a 36 card deck. So that being the case, that's why, for example, getting any particular combination of these, all you're doing is adding up the number of ways this can happen and dividing by 36. Okay, so that's where this chart is coming from. But then to turn it into this even and odds case, what we're noting here is that to get even, any one of these 9 possibilities will give you even followed by even. There are 9 ways. Somehow that got left out. There are 9 ways of getting even followed by even out of 36 equally likely rolls. Therefore, the probability of even is 9 out of 36, or 1/4, or 0.25. The same is true of the others. Even, odd, even. If you could go through them all and list all the outcomes if you want to, just to prove it. And so what we end up with is 4 equally likely outcomes of our experiment when we roll the die twice, but we only pay attention to the evens or odds. Okay, so this is the logic behind why we can claim that each of these is equally likely to occur. All you have to do is go back to the original outcomes and count them up. All right, so with the understanding that each of these is equally likely to occur, then we can go ahead and calculate anything we want. Or suppose, for example, that you were interested in knowing the probability of getting doubles. Okay, well, how would that work? Again, if you're playing Monopoly, you remember doubles are good news in Monopoly because you get another turn. Unless, of course, you get 3 in a row, then you go directly to jail, which is very unfortunate because then you're wasting your time in jail, not buying properties. So as another example, that was the most frustrating part of the game, jail. As another example, suppose you want to calculate the probability of getting doubles when rolling the die twice, or rolling 2 dice. The doubles consists of, and then you just list them all: 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Since there are 6 ways of obtaining doubles out of 36 possible outcomes, the probability of getting doubles is 6 out of 36, which is the same thing as 1 out of 6. Or if you want to give it a decimal version, it's 0.167 approximately. Okay, so in a case like this, probabilities are fairly easy to calculate when all the possibilities are equally likely. Now, if I asked you a different, like for example, from this chart, this is the part that's not equally likely, the sums. The actual rolls are equally likely. It's the sums that have different probabilities. So imagine the following situation. Suppose I told you that I'm playing a game of some kind where I can only win a prize if I get at least a 10. All right, so as another example, what is the probability of getting 10 or more when rolling 2 dice? Well, the probability of getting exactly a 10 equals the probability of getting either 4 and 6, 5 and 5, or 6 and 4. The probability of getting an 11 equals the probability of getting a 5 and a 6, or a 6 and a 5. And the probability of getting a 12 is, you need, for that, you need 2 6s. That's the only way that can happen. This first one has a probability of 3 out of 36. This one would have a probability of 2 out of 36, and this one would be 1 out of 36. So therefore, the grand total would have to be the sum of those 3 probabilities. In other words, therefore, the probability of getting 10 or more equals so we've already seen that that's 336 plus 236 plus 136 equals 6 out of 36, which is 1 out of 6. Or if you want to use decimals, 0.67. So you can see, you get the idea or how we're calculating these probabilities. It's all based on the way the original experiment was conducted. Okay, so because we're rolling 2 dice, we know that right from the beginning, there are 36 equally likely outcomes, and we can use that information to calculate any probability that we might need. Now, all of these, by the way, are what we would call theoretical probabilities. Based on the distinction they made in the video, these are all theoretical probabilities based on our knowledge of how the dice are constructed. Now, what if we didn't understand how the dice work? Let's say there's some reason why we can't do this. You could use empirical probabilities could be determined by rolling the dice twice, many, many times, and gathering up information, or summarizing the results. And then you would have a table. And then let's say, for example, suppose that the experiment of rolling 2 dice is repeated 1,000 times with the following results. Okay, and so you actually do this. You sit down and you've got nothing else to do one weekend, and you say, I don't understand how dice works, so let me sit down and practice. Let me just roll them. And what I do, so for this, I'll steal this chart. The results are shown in the following. Yeah, okay, good. So let's say in the first case, I get, let's see. How about if I get 3? And then for this one, I get 5. And then for this one, I get 9. And 13. Well, that's actually too low for 1,000. Let me try 30, sorry. 30, 50, 90, 132, and 201, and 224, and 198. Wow, it's tough to do this on the fly. 140. Okay, I better stop for a second and make sure I've got enough left. 30. No, I didn't do it very carefully. I've got too many. Let's make this one 161, and this could be 190. All right, let's see if that works. But you can see what I'm doing here. I'm trying to imagine a situation where we're just sitting there and trying to figure it out just by repeating this experiment, and it's still too much. All right. Yeah. Yeah, I don't want to waste all day with this. It's just, it's so difficult to plan this out properly. All right, let's see if that works. All right, that's better. Okay, so let's say this is what we came up with. So what this means then is that unlike the theoretical probabilities, this is what we actually wound up with. So these all have to be divided. Now, this is 0.3%. Let's see. No, that's not right. That's 3%. Now, of course, you know, when you roll the dice like this, anything could actually happen. And you can see they're not really the same as what we got with our theoretical probabilities. But this is what often happens in practice. They're not going to be exactly the same. And so because this is empirical, this is based on experience rather than our theoretical knowledge of what's going on with the dice. Okay, now like up here, for example, I guess what I could have done is figured out these as percentages. This is 2.8%. This is 5.6%. Let's see, this is 8.4%. This is 11.1%, 13.9. This is 16.7. And then now we can just go through these again. By the way, if you wanted to really do this experiment of the dice, there's a way you could do that. You could go into Excel. If you really have a good feel for Excel, you can have it generate random numbers and do experiments just like this. So these are the theoretical probabilities. So what I'd like to do is compare them side by side. Ooh, that's going to be tricky. Yeah, maybe not right now. I don't want to take all day with this, but if you compare them side by side, in fact, you know what I could do instead? Why don't I just get the other one so we can just sort of look at them together side by side. Just so you can get a peek at how they compare with each other. I don't think it's possible to show them side by side on this. Well, maybe it is. Let me just see what I can do. These are the empirical probabilities. And these are the actual probabilities, or theoretical. Okay, if I do this properly, I might just be able to show them to you side by side. Okay, so you can just about see them. You can see, here we go. That's not too bad. You can see they're not like radically different from each other, but they're not identical either, are they? So the whole point of this is that the theoretical probability is on the right. The empirical is on the left. Empirical means we just roll a die 1,000 times and see what happens. On the right, these probabilities were determined by our knowledge of how the dice work. And so you can see the two are similar, but they're not identical. So hopefully this will give you a sense of what we're referring to with theoretical and empirical probabilities, like in the video. And by the way, what's interesting about this is that if we roll the dice even more than 1,000 times, the more we roll the dice, the closer the empirical probabilities will come to the true probabilities or theoretical probabilities. So let me just throw that in there as well, because that's an important detail. We repeat this experiment, the more frequently the experiment is repeated, the closer the empirical probabilities will be to the true or theoretical probabilities. Which is good, because this is helpful information, because if in practice it is not feasible to determine the theoretical probabilities, then we can have confidence in our empirical probabilities. In other words, we know that we don't have enough information to do the theoretical. So instead, we lean on our empirical probabilities. But if we calculate them correctly, well, that's okay, because we know that they'll get very close to the true or theoretical probabilities. That's very encouraging, because the whole point of statistics is to take information and draw conclusions from it based on some information that we may not have. Okay. So, by the way, just as a fun thought experiment, remember way back here, we kind of got lost along the way. We had the 4 outcomes. When we roll a die twice, but each one we only care about even or odd. What's interesting to think about is, what if we roll the die a 3rd time? How many different possible outcomes could there possibly be? Well, it turns out that every time we roll the die again and only focus on evens and odds, that doubles the number of possible outcomes. Now, I'm going to prove that to you with a very interesting diagram that we'll need later on, called the binary tree. And this is a graph that shows all the different possible things that can happen when we carry out an experiment like this. And so you can see in the beginning, we can have an E or an O. And then when we have a second roll, these are all the possibilities which have been discussing. But with the third roll, we have 8 possibilities, as I mentioned before, and here they are all lined out nice and neatly for us. How do we know? For example, once we have an even, the next roll could be an even or an odd. If we have an odd, the next roll could be an even or an odd. So in other words, we're simply listing all the possibilities. If we have 2, for example, evens, the next roll could be another even or an odd. And we work our way across, and we have all 8 of them. And because each of these is equally likely to occur, as we've seen, each of these 8 has a probability of 1/8 or 0.125. All right. Does that look, now this is an easy way to keep track of the outcomes of an experiment, as long as it's not too complicated, of course. It's called a binary tree because there's only 2 possible outcomes each time we repeat the experiment. All right, now once all this is in place, when we conduct an experiment, what we're going to do is gather up all the outcomes that could occur, and we're going to give it a special name. We're going to gather them up into a special set, which is called, okay, let me give you a minute to catch up, and I'll tell you what the special set is called. By the way, I just want to mention in passing that probability theory ultimately is based on set theory, which you've been exposed to. And maybe we'll do a little quick review here of sets. But for any experiment, the list of possible outcomes is gathered together into a special set, which we call the sample space. So the sample space S is simply a set that contains all the outcomes that could occur when we conduct this experiment. All right, so there you go. It's a set. It contains all the outcomes. Now, I did mention that this is what we're going to do in this chapter is based on set theory. So I'd want to do a very, and I mean very quick review of set theory. So let's do that real fast. Now, I say set theory, I basically mean algebraic operations that could be performed on sets. Okay, so let's take a quick look at sets. Now, first of all, we've got 4 sets listed on top here. A is 1, 2, 3. B is 2, 3, 4, as you can see. C is just 5, and D is 1 and 2. Now, some of this stuff you may have seen before, possibly not, it depends. But what can we do algebraically with these sets? We can perform operations that are equivalent in certain ways to what we do with real numbers. But the analogy isn't perfect. For example, here's something called union. And what it's telling us to do is simply create a new set out of the 2 original sets. Just bring them all together. All right, so if we start out with 1, 2, and 3, and it's set A, 2, 3, and 4 is set B, I'm creating a new set that contains all of these elements. But if you notice, I don't list any of them twice. In other words, you see how there's a 2 and a 3 in both sets, and yet I only have them listed here once. Okay, so the convention is to only list the elements that appear in either one or the other or both. And if you've not seen this word union or this symbol, some books use the English word or to describe what we've just done. Okay, so either you've heard of this as A or B, or you've heard of it as a union B. Or maybe you've never heard of this before at all. Does this look familiar at all? I don't know. It doesn't matter. We'll go through all of them. And then we also have this other operation that we can perform on sets. Okay, I'll give you a minute to catch up, and then we'll take a look at this next one. And again, it might ring a bell when you see it. And what is it? This time we're going to perform an operation called intersection. Oh no, what could that possibly be all about? Let's find out. Okay, so first of all, the symbol is different. The concept is very different. So I'm taking the same sets. The intersection of A and B is a set that contains, oops, I just realized there's a mistake in here. 2 and 3, because those are the elements that they have in common. So the symbol is this upside down U, which we call intersection, or sometimes some books use the English word and to represent intersection. Okay, so what else is there that you may have encountered in your past math travels? Here's another possibility that you've seen or not seen. If not, it's okay. We're doing it right now. And that is the concept of subset. Now, if you look carefully, it says DNA. All the elements in D are also elements of A. And so we say that D is a subset of A because all the elements in D are also elements of A. You can think of, there's a million examples you can think of. For example, the odd numbers are a subset of the real numbers. That would be an example because all the odd numbers have to be real. All right, let me show you a very quick example of this in the real world. How about this one? What if I define the event A to be a set that contains not numbers, but students? And the same thing with set B. All right. So let's say, for example, my first set A consists of all the students at SUNY Purchase. And then set B is all the art majors at SUNY Purchase. I think you'll see that B is a subset of A because everybody who's an art major at SUNY Purchase must also be a student at SUNY Purchase. And this is all that it means. One is contained within the other. All right. In fact, I'll tell you what, let me just do this real fast. You've probably seen this before. A good example of subsets in the real world comes from something you may have seen. You may have seen these Russian dolls. What is this all about? These dolls, you see how each one is just a smaller version of the previous one? Each one of these in math could be considered a subset of the other dolls. In other words, all these little dolls are subsets of the big doll. All right. So have you ever seen these before? They all fit right inside of each other. So when you open up the big one, it contains all these little ones, and they're called Russian dolls. That's probably not the formal name, but that's what we tend to call them. Okay. Russian dolls. Everyone knows what they are because it just means all the dolls fit inside of each other. They're all subsets of each other. So that would be a real world example. And then finally, let me show you the opposite of subset. Suppose I have two sets like C and D. C contains 5, D contains 1 and 2. Clearly, 5 is not an element of 1 and 2. So here we simply say that C is not a subset of D And we'll illustrate that with the symbol, the subset symbol with a slash through it. Okay, so that's our brief review of set theory. And from here on, we'll define some important new rules. What we're building up to here is how to calculate rules for calculating probabilities, especially with more complex events. All right, so wow, boy, that went fast. I thought that was a lot of fun, today's class. We were introduced to a lot of key concepts, some of which you may have been familiar with, some of which you might have forgotten, but that's okay. It's all coming back, isn't it? Man, that's a lot to do on a Monday morning, isn't it? But that's okay. It's almost like that's working out before you do something. The rest of the day, you'll feel very fit. Well, if not physically fit, you'll certainly feel mentally fit to take on whatever comes along during the rest of the day. So I'd say we should stop right here, and we'll pick it up next time with chapter 11. All right. Unless there's any last minute questions, I'll see you all next time.
Bye. Thank you, Professor.
Okay,
Thanks.
bye. See you next time.
Thank you.
Thank you.
Bye.